Hello and welcome to this learning module in which we are going to discuss about the distance protection of transmission lines. In this module, we will discuss about the basic concepts of distance protection. We will discuss about the operating principle of the distance protecting relay, the effect of infeed and the fault resistance, that is the effect of infeed and fault resistance on reach setting. And finally, we will discuss about the coordination of distance protection relay in a complex transmission network. Along with this, we will also discuss about the various distance protection characteristics. That is, we will discuss about the rectangular, quadrilateral, Moe, offset Moe, lenticular, etc. In the end, we will discuss about the effect of infeed and pre-fault power flow on the performance of distance protection relays. So, before starting this session, there are 3 to 4 assumptions that I am making. I'm assuming that you all are aware about the various fault analysis techniques. You are aware about the uh, positive sequence, negative sequence, and zero sequence impedance. You are also aware about how these sequence networks are connected for various types of faults. So, the generally, in the transmission lines, there are two types of fault. One is called shunt fault and the another is called series fault. These are two types of unbalanced faults. In case of shunt fault, these can be single line to ground fault, line to line to ground, three phase or three phase to ground faults. In case of series fault, it can be open circuit fault, which is also called local conductor. Now the analysis of this unbalanced fault, that is LG, LL, LLG. These types of faults, the analysis of these types of faults are generally done by sequence networks. And the transmission line sequence impedance have positive sequence, negative sequence, and zero sequence. Generally, the positive sequence and negative sequence impedance are equal, and the zero sequence impedance are 2.5 to 3 times of positive sequence impedance. Also, you must be aware that whenever there is a fault on transmission line, so suppose this is your generator, along with this is your generator transformer, then your transmission line. After that transmission line, you will be having another transformer over here, then the distribution lines, and finally the load centers. So the network, if you draw, it can be generator followed by this, or you can write the simple terms. You can write this as a voltage source along with the source impedance ZS, then the transformer impedance ZT, then the transmission line impedance ZL, and then the distribution line impedance, so distribution transformer, and then this load. So this is the general configuration. Now suppose there is a relay which is installed at this point. So this is your bus at which you are using a transmission relay. So generally, suppose these two impedance, it is ZS. So now, if you calculate the total load current from this source to this load, IL, what is this? It will be Vs divided by ZS plus ZL plus ZD. This will be your IL equals to Vs divided by this. Now, in case suppose there is a fault at this particular point, so now this impedance up to this fault point will be ZS plus a part of line impedance. So your total current will be Vs divided by ZS plus X times ZL. And if you see this impedance, which is much lower than this, so your line, this IF, the fault current will increase. And this is generally what happens in case of your shunt fault. So now current increases, and if you measure the voltage at this relaying point VL, it is or VRL or VRM. This is simply Vs minus IF into ZS. So if this IF increases, so your relaying point voltage will drop. So based on this, you can say that in a shunt fault, generally what happens in this case of shunt fault, your current increases and voltage drops. Based upon these two, current or voltage, you can have different types of protection system. So we can have overcurrent, we can have under voltage, we can have based upon the ratio of this voltage and current as impedance or under impedance protection. In this session, I will discuss only about this last protection, which is the impedance-based protection. So now the various very simple operating principle. So consider this is a source impedance Vs, source voltage Vs with an impedance Zs. The transmission line impedance ZL, and this is a load. So now a relay is installed at this relaying point. So what is the measured impedance by this relay? So the impedance measured by this relay will be VR divided by IR. And what is IR? So basically IR is equals to VS divided by your VS divided by ZS plus ZL. So or plus Z load you can also say. So this is your simple VIR, and the VR is equals to, what is VR? VR is equals to, can write IR times ZL plus Z load. So ZR we can write as VR divided by IR equals to ZL plus Z load. So that's why it is same over here that ZR is equals to ZL plus Z load. Now suppose there is a fault at this point. So when there is a fault at this point, what will be the total impedance measured by the relay? ZR is equal to again VR divided by IR, and that will be VR divided by, what is IR? IR is basically a sum of IF plus IL. So VR divided by IF plus IL, and generally the fault current is very high as compared to load current. So we can write ZR is equals to VR divided by IF, and this will be M times ZL. So if you see over here, the impedance measured by this relay is a fraction of impedance up to the fault point. So the impedance, total impedance measured will be the impedance up to the fault point, which is a fraction of total line impedance. So if you plot this on this Z real imaginary plane, that is RX plane, so what you will get, this is a Z at some angle. So this is your Z, and up to this point this is your fault impedance. So the relay generally calculates the impedance up to fault point, and it will take the decision based upon this impedance. Now fault resistance. So what is fault resistance? Basically it is the arc between the faulted conductors. Ground fault resistance, it consists of arc resistance between conductor and tower plus tower and tower footing resistance plus ground return path resistance. Fault resistance may be particularly large in the case of tree contacts and conductor lying on the ground. Tower footing and overhead shield wires affect ground return impedance, and generally the ground fault resistance are much greater than phase fault resistance. This is an empirical formula for calculation of fault resistance or arc resistance. So our arc is equals to a 28707 into L, which is a constant, divided by I to the power 1.4. So you can see that the arc resistance is inversely proportional to your current or actual fault current. This, and if you see this, if this is a transmission line AB, so the minimum fault current will be for a fault which is closer to remote bus. So when there is a fault closer to remote bus, your arc resistance magnitude will be very higher. So now these, if you now include the effect of arc resistance or include of the effect of fault resistance into the path. So what will be now the total impedance measured by the relay? The total impedance measured by the relay will be M times ZL plus RF. So what does this means? This means is that this is your earlier actual M times ZL up to this point plus some RF. So this is your MZL plus some RF. So if you take this resultant, it will be somewhere at this point. What does this means? This generally means is that if you are using, suppose, a characteristic, circular characteristic, then earlier, if you draw this circle with the radius is equals to, the radius of this circle is equals to Z by 2. Z is equals to the impedance of the line. So the diameter is the line impedance. So if you draw the circle with line impedance at the diameter, then the relay will measure the impedance up to the fault point, or impedance the total transmission line. But now when we include the RF, so this impedance measured will shift from this line angle to some other angle. What does this means? For a short line, your this circle will be smaller, and in that case, your ML plus RF might come outside the circle, and this distance protection relay might not work properly. So in that case, what we have to do, we have to implement a characteristic with fixed magnitude of x but a variable r. Generally, we are not using circular characteristics or more characteristics for because of these limitations. Because in a circle, if you can recall, this circle equation is x minus h square plus y minus k square is equals to r square, or you can write as x square plus y square is equals to r square. So if you want to vary any of these parameters, so if you want to vary either x or if you want to vary either y, it is not possible. So in order to make a circle, in order to have a circle, if you increase the r, so both coordinates x and y must change. So if you want a higher magnitude of fault resistance without changing impedance, it is not possible. Without changing reactance, you cannot change the resistance coverage. But the reactance is fixed. The total line reactance is fixed. That's why we are using a characteristic in which we can fix the reactance and we can directly change the resistance coverage. That types of characteristic is called quadrilateral characteristic. So a distance protection characteristics, basically there are multiple characteristics. First of all, this is a simple impedance characteristic in which a circle is drawn with the radius is equals to your ZL by 2, and this characteristic is very simple. Any fault inside this characteristic, the relay will operate. Any fault outside this characteristic, relay will not operate. But the limitation is that this characteristic is non-directional, so it cannot detect whether the fault is in the forward direction or whether the fault is in the reverse direction. It is directly going to issue a trip command whenever the fault impedance locus falls inside this characteristic. So we move on to the next characteristic, which is more characteristic. It is inherently directional. The only thing is that now the circle is shifted so that it is drawn from passing through origin, and now the any fault in the forward direction only will be detected by the relay. No fault in the reverse direction will be detected by the relay. But the limitation is that suppose there is a fault which is closer to our bus, closer to the local bus, a three-phase fault. In that case, the voltage available to the relay will not be very high, and the relay cannot detect a fault closer to this point, whether it is in the forward direction or it is in the reverse direction. So to include that, we use offset mode characteristic that has some offset in the reverse direction, and this is only to take care of the closing faults. But if you see both these all these three characteristics, the thing is that all these characteristics have high resistive coverage. But due to this high resistive coverage, there is a chance that these types of characteristics might maloperate during your uh, load encroachment. What is the meaning of load encroachment? Basically, in simple terms, you know that Z is equals to V by I, and suppose your load is increasing. Suppose load is increasing, and increasing. Then suddenly your Z will keep on decreasing, and for some point it might happen that your load characteristic might enter inside the uh, characteristic of your protection zones, and it might maloperate. So to take care of that, a lenticular characteristic is used, which is offset mode, which is compressed from both sides, and now if you see the this area is trimmed, and that's why this is not going to be affected during the load encroachment period. The next is quadrilateral characteristic, in which we can have a fixed reactance reach with a variable resistive reach, so it has a high resistive coverage. And this type of characteristic I have already explained in the last slide. But nowadays, which characteristic we are using is this polygon characteristic. And if you see the advantage, the quadrilateral characteristic, it has a high resistive coverage, but again, in case of load encroachment, this might maloperate. So we have to cut a portion of the characteristics depending upon the load characteristic, and this is for the load encroachment region. And another thing, if you see in this characteristic, the top part is inclined at some angle, and this is to take care of the pre-fault power flow direction. Nowadays, this is made dynamic, and we will discuss about this dynamic characteristic also in the coming slides. Moving on, the zones of distance protection. Generally, if suppose this is a transmission line AB, so this is a transmission line between two substations. So this is transmission line A, B between the substation. What is our requirement is that we want to protect this whole transmission line with minimum time. So that minimum time is 0 millisecond, and we want to protect this whole transmission line. So we can set a single zone. We can set a single zone with 100% coverage and t is equals to 0 millisecond. But generally it is not possible. Why? Because Z is simply a ratio of voltage and current. Now from where you get voltage for your relay? We get the voltage from CVT. From where we get the current? We get the current from CT. Then the relay internal processor, it will calculate the Z, the ratio of voltage and current, and within this conversion what it uses is your this sampling, that is the analog values are sampled, then quantized, and then normalized for digital nature, and then using the A by D converter it determines the magnitude of voltage and current, and then finally it will calculate the V by I. So these three factors, one is CVT, another is CT, and then the next factor is relay processor. After that, it will compare this calculated impedance with the line impedance, and if this is less than the setting, then it will issue a trip command and it will give you the fault location. So there are generally four parameters. One is the inaccuracies of CT. So you will have the inaccuracies of CT, CVT, relay processor, and the line parameters. So generally these four parameters can have some error either in the positive direction or in the negative direction. Based on this error magnitude, your impedance calculated by the relay will keep on changing. So what happens, generally we can consider that all these errors are, it is standard practice to assume that these errors are in the plus minus 5% direction. So the maximum error due to this maximum error can be plus 20%, and the minimum error can be minus 20%. So because of this, now we cannot set a single zone with this AB with 100% transmission line length, because suppose this is a 100-kilometer line length and we set zone 1 as 100 kilometer. Now what happens if all this error contributes in the positive 20%? So we might reach up to this point. So the relay apparent impedance might reach up to this point of 120 kilometer. But this is not the principal line. This is beyond the principal line. So your relay might operate for the out of zone faults because of this 100% setting. So the maximum possible setting of zone 1 can be 80% only, because if you set 80%, then even if all the error contribute to 20%, so it might reach only up to the remote bus. So now we will discuss about all these factors. First of all, several zones are set to protect a transmission line and to provide backup protection of remote bus. Why? If you set this as zone 1, then you have to set another zone now for this to protect this area. But again, you cannot set this exactly 100%, because suppose now all error comes to minus 20. So again, we will reach only up to this point. So you have to extend this to suppose 120%. 120 minus 20, you will reach up to this remote bus. So these all types of zones are called backup zone. First, zone 1 setting less than the full line impedance to prevent overreaching the effect of load, fault impedance, fault contribution from the remote terminal, and error in instrument transformer. The second zone, designated as zone 2, is to set to protect the remainder of the line plus an adequate margin. So zone 2 is for this with an adequate margin. Zone 3 is the backup of the longest line from the remote bus. So now these various zones. So consider this substation A and substation B. The zone 1 from this substation will be 80%. Zone 2 generally 120% of principal line, and zone 3 is this transmission line, principal transmission line AB plus the longest transmission line, suppose from the remote passage BC into 120%. Generally, zone 1 will be instantaneous. Why instantaneous? Because this is to protect the principal transmission line. Zone 2, it cannot be instantaneous, although it is protecting this principal transmission line, but it also have the coverage for the next line. So it will be some time delayed zone, and that's why it is backup zone. Zone 3 is also backup, and it will be also time delayed. Now, the reach of zone 1. So suppose this is substation A, B, C, D, like that. So the zone 1 of the relay at substation A will be 80% of ZAB. Zone 2 from this for this relay at A will be 120% of the principal line, that is 120% of ZAB, and the zone 3 it will be 120% of ZAB plus ZCD. Now zone 1, it trips the circuit breaker without delay as soon as fault within zone 1 reach is detected, and resetting is limited by these four factors that I have already explained. Zone 2, it covers last 20% of the line which is not covered by zone 1, provides backup protection for remote bus bar because this is the area of zone 2, so it covers this bus bar of remote end. Zone 2 is time delayed because it also covers this a portion of transmission line which is outside the principal transmission line. Now the important thing, the time settings of a long line followed by several short lines. What does it mean? Suppose you are having one long transmission line of 100 kilometers followed by a short transmission line of suppose 10 kilometers. In that case, this is zone 2 of the relay at A. Zone 2 relay at A will be 120 ohms, suppose 1 ohm per kilometer. But the zone 2 at this B relay for BC line will be 12 ohm. So now suppose there is a fault at this, and this is at 9 kilometer. So this 9 kilometer is in the zone 2 of BC. Also, this is in the zone 2 of line AB from A end. So there is a race around condition between the zone 2 at this relay and zone 2 of this relay. To avoid this kind of problem, generally the zone 2 of this substation A is time graded with zone 2 of this. Generally the zone 2 is set as 350 millisecond. But whenever there is a long line followed by short line, then to avoid this zone 2 to reach into the next section, generally either the reach is changed. So now how the reach is decided? So now the reach is decided, it will be your zone 2 will be principal transmission line plus 50% of adjacent shortest line. So this is one method, or what else we can do is we can time delay zone 2 by 500 millisecond instead of 350 millisecond. Moving on, zone 3. Zone 3 provides backup for next adjacent line. So if it is your zone 3 transmission line, 2 transmission line to 3 substations, so the zone 3 will be up to this point, that is ZAB plus ZBC into 120%. And this is generally to take care of the relay failure at this location, or to take care of any types of problem, so that you are considering the longest line. So in case of the problem, the longest line, and it is not able to protect, then the relay at A will clear the fault. So this is again backup, provides backup protection for bus bar. Actual zone 3 setting will be scheme specified, that is permissive or blocking. We will discuss it in the later slides. And modern numerical relays have 3 forward and 1 reverse looking zones. Now the effect of Infeed on reach setting. So up to this point we have discussed only this, simple concepts. What is the meaning of zone 1, what is the meaning of zone 2, what is the meaning of zone 3, how we calculate the reach settings of zone 1, zone 2, zone 3, etc. Now consider uh, four bus system, that is M, N, P, and T. These three sources, one at bus M, one at bus P, one at bus T. Now the relay at this bus M is Rm. The current flowing from this bus M to N or up to the fault point will be Imn. Similarly, Itn from this source, and the impedance of line Mn is Zmn. Impedance up to this fault point for the fault at F is Znf from this bus N. Now, what is the voltage at this relaying point? So, voltage at this relaying point, that is Vm, is equals to Imn times Zmn plus Znf. So, Imn times Z1Mn, Z1 means positive sequence, plus INF times Z1NF. We are considering only the positive sequence impedance. Now INF, so this current INF from this bus N to the fault point will be IMN plus ITN. So INF is IMN plus ITN. What is the meaning? Then the VM, so VM will be IMN times Z1MN plus INF means ITN plus IMN times Z1NF. So the impedance measured by relay will be Vm, that is the voltage at this bus divided by Imn. So Vm is your this magnitude divided by Imn. So now this Imn cancels out, and so this becomes Z1Mn, and then this Imn, it will be 1 plus Itn by Zmn. What does this mean? This means if you consider this Itn is equals to 0. So if ITN is equals to 0, then this Zm measured impedance by the relay will be Zmn positive sequence and Znf positive sequence, and this is correct. So if there is no infeed, then the impedance measured by this relay will be impedance up to this fault point, and which is what we expect in general. But not due to this infeed, the actual impedance measured by the relay changes. So the actual impedance measured by the relay increases due to this infeed effect. So this impedance Zm measured by the relay, or it is also called the apparent impedance measured by the relay, that Z apparent, it becomes higher. And once this impedance becomes higher, so there is an underreach problem, and it depends upon the strength of the source at T and its position. What is the meaning of underreach? Underreach basically means now this actual case, suppose your fault is at zone 2 or fault is at zone 2, but the relay sees the fault in zone 3. So this is called underreach. Underreach. This is the actual fault and detected by relay. Why it is underreach? Because the fault is at suppose 100 ohm, but relay sees that the fault is at 120 ohm and it is not going to operate. So this type of problem is underreaching. There is no issue with zone 1. Why there is no issue with zone 1? Because zone 1 is only up to 80% of the principal transmission line, and this 80% is always before this your infeed effect. So zone 1 is up to this point, so it is not going to affect it with infeed. Now zone 2, it will definitely have the effect of infeed, but in any case that effect of infeed is not going to be such that, so your zone 2 is not going to reduce below this remote bus, because even if this has the maximum effect, it will be only up, it will reduce the zone 2 coverage only up to this point. So infeed reduces zone 2 coverage but never underreaches the remote terminal. But zone 3, it has the maximum effect of infeed, and you have to set this according to infeed amount with a stronger infeed. So the infeed, if the infeed increases, so that apparent will increase. That means we have to set the higher coverage of zone 3. If you increase the coverage of zone 3, then the problem of load encroachment comes into picture. So these are the problems related with your infeed, the problem of coordination. So you have to take into a lot of things into consideration. The problem of load encroachment, problem of infeed, all things are coupled together. Now the effect of fault resistance. We have already discussed the effect of fault resistance earlier, but now we will discuss in more details. This is the same picture that I was using over here. So two bus M and N I have shown over here, bus M, bus N. The relay at point bus M is Rm. The impedance up to this fault point of the transmission line impedance is X times Zmn, and remaining impedance is 1 minus X times Zmn. Zmn is basically the impedance of the transmission line, Z, or impedance transmission line Mn. So the fault current IF is equals to Im, Vf is equals to the fault voltage VF is equals to IF times RF, and your VM, the voltage measured by the relay, will be IM times RM plus X. Uh, sorry, this IM times XZMN, IM times XZMN plus IM times RF. So why IM times RF? Because it is VF. So VM will be XZMN plus RF into IM. So the impedance measured by the relay will be VM is equals to XZMN plus RF. What does this mean? This means simply this is your XZMN in general, but now because of the introduction of RF, your impedance measured by the relay changes. So the fault resistance changes the total impedance measured, and now it moves into the direction of resistance. And so this effect is generally, in case we are considering the source only at one end, we are considering that this is a radial system. So in case of radial system, the effect of fault resistance is in the resistive direction only. But in case of complex transmission system, in case of complex grid, uh, all these systems are not radial, but these are ring connected or mesh network. So now we are considering the source at both ends, source at M and source at N, and this XZMN is the impedance up to the fault point. 1 minus X10 ZMN is the impedance, remaining impedance of the line. IM is current contribution from bus M, IN is current contribution from bus N, and this RF is the fault resistance. So now IF will be IM plus IN. So VF is equal to IM plus IN times RF. VM is equal to IM times X ZMN plus IM plus IN times RF. So VM by IN, that is the impedance measured by relay, will be Vm by Im will be x times Zmn plus 1 plus In by Im times Rf. Now, in case of a AC system, we know that the power transport will be Vs Vr by x sine delta. Delta is the angle difference between these two buses, sending and receiving end voltage. So now if the power is being transported from bus M to bus N, that means what happens? The voltage at S leads the voltage at bus R, or in terms of current we can say that Is leads IR, or we can say that IM leads IN. Similarly, if the power is transferred from N to M, this is the power flow direction. Now the power flow direction is this, then IN leads IM, or IM likes IM. So the first case, when the power is exported from M to N, that means IM leads IN. This is the same case. Second case, when power is imported at this bus, at that time IM lags IN. So now this, because of this, the IM divided by IN ratio will have resistance as well as reactance. So what happens? In case of power import, so your IM lags IN. That means IN by IM will have R plus JX. When IM leads IN, then your IN by IM will be R minus JX, and in case power is, or In is equals to 0, in that case it will be a flat line. So this is simple case of source at one end only, when the power flow, bidirectional power flow, before uh, fault power is in the import, so In is lagging, In is leading Im, and that's why this reactance will increase. When power is exported, this reactance will reduce. So now you can see that the effect is in both R and X. So now if I plot this, this is your zone 1 rectangular characteristic, this is zone 2. In general, this is the impedance measured by the transmission line. Now with the introduction of fault resistance, if there is a reverse flow of power. Now, what is the meaning of reverse flow? That is, bus M is importing power from bus N. So now IN is leading IM. So your this reactance will increase as well as resistance. So now you can see that even if the fault is in the zone 1, relay is seeing this fault in zone 2. So this is an underreaching problem. Similarly, for forward fault, now what happens? For even if the fault is in zone 2, relay might see the fault in zone 1. Uh, it might happen that for a zone 1 fault, if your fault resistance is very high, so in case of your power flow in the forward direction, relay might not see the fault correctly, and your coordination becomes very difficult. These types of things are generally taken care of in case of modern numerical relays through dynamic characteristics, and the distance protection characteristics are made dynamic. So the main point to consider over here is that if you consider the effect of infeed, so the effect of infeed generally no effect on zone 1, no effect on zone 1, but in case of only radial feeder, if you are considering the source at both ends or pre-fault power flow conditions and with high resistance fault, then the infeed might change the apparent impedance measured to such a value that relay might not detect a fault and relay might not operate. Similarly, if your power is being exported from one bus or bus to bus N or from local to remote end, and this is a fault involving high resistance, in that case it might happen that the relay sees a fault of zone 2 in zone 1, and this is called overreaching problem. So this is your overreach problem. Your relay might have an underreaching problem in which it sees a zone 1 fault in zone 2, and this generally happens with high resistance fault with pre-fault power import at our bus. So in this module, generally we discussed about the basics of distance protection. We have also discussed about the various types of distance protection characteristics. We have discussed about the reach settings of zone 1, zone 2, zone 3, and thereafter we have discussed about the effect of fault resistance, the effect of infeed, the effect of pre-fault power flow on the distance protection zones. We have also discussed about the settings of distance protection when your long line is followed by short lines, then how the zones are determined and how the settings are done. I hope the concepts explained in this session are clear to you. In case of any doubt, you can always comment in the discussion forum, or in the you can directly mail to my email ID, so that based upon the queries received from your side, I will try to resolve all the dots. So now I will conclude this session up to or up to this point only. So thank you for watching this e-learning module.